All right, so I put together kind of a list of things. Oh, there it is. That hello. Um, we just started. Um, I'm just about to show you guys uh, a list of, I guess, exactly what's going to be on the test. It's probably something you already covered. So this is basically what this is what's on the test and what you kind of need to know. So I guess for problems, we're going to have 6 derivative problems and 6 integral problems. And these are kind of the things that we're going to need to know to complete those things.
Yeah.
We're going to have a linearization problem, a tangent line problem, a definite integral problem, finding the area between 2 curves, related rates, an initial value, and a min-max. And then there are 2 conceptual questions at the end that are going to ask you to write a little bit about what you understand about a couple of the concepts that you've learned the past week. I guess since this is for you guys, I guess we can start with whatever you want to start with. If there's something you feel like you need to work on more than others, I'm comfortable starting wherever. Is there something in particular that you want to cover?
Could we start with the initial value problem?
Yes, we can. So.
And I want to ask you about tangent line problem too. Actually, to me, it is, I don't know how to distinguish between linearization problem and tangent line problem.
Yeah,
so that.
Yeah, they're very similar. It's almost the exact same problem. It's just the linearization has a couple extra things tacked onto it. Yeah, so we can cover that too. So I guess we'll start with the initial value problem. So let's say we have something, I don't know, let's say we throw a ball and it's traveling in a straight line and its velocity is described as such. And so we want to know the position function. So this is the velocity function. So we want to know the
Hey David.
Yeah.
Sorry to interrupt. I think you're still sharing your screen.
Oh yeah. Sorry. Yeah. So I can.
Really small. Perfect. Okay. There you go.
That better?
Yeah. Awesome. Thank you.
All right. So now we want to find the position function, and we know that our position function, s of 1, so we'll call our position function s. We know that equals, let's say 10. So given this information, we need to find our initial function, or our position function. So the way that we're going to start this one is we're going to take the integral of this problem. So we want to find our s. So we're going to take the integral of this. All right, so I was going to separate this into 2 integrals. So we have the integral of 36 plus the integral of 60 over t plus 1 squared, and those will be dt's. So this one's really easy. So this is just 36t. And then this one, we can take this 60 out. So we will put the 60. We can, since it's a constant, we can take it out of the integral. And then so we'll have the integral of t plus 1 to the negative 2 dt. All right. And so I guess since this is kind of weird since it has a chain, but then essentially you dt. So then we just have u to negative half for, so that would be u to the negative 1 over negative. So 36t plus 60 times t plus 1 to negative 1. This is actually going to be a negative. Does that make sense how we got to this point?
Kind of. Would you be able to kind of just walk through one more time what you did, like at each step?
Yeah. So we started with our integral up here. So we want to find the position function. We know that velocity is the first derivative of position.
Right.
So we're going to take our derivative of our integral of our velocity. And then so it's this equation. And so I separated it into two different integrals because of this plus sign. I can do that.
Right.
So then the integral of 36 is 36t. And then, so on this problem, 60 is a constant. So I just pulled it out of my integral. So I have this integral. And then to just make it kind of simple to see, I used the u substitution problem.
Yeah.
So u is t plus 1, du is dt. And so we can just replace dt with our du and our equation with u. So we have u to the negative 2. And then we add 1 and then drop it to our thing. So we end up with u to the negative 1 over negative 1. So it turns it negative, which is what happens over here. So when we put the pieces back together, we have 36t minus our 60 that we pulled out times our u to the negative 1 power plus c.
Mm-hmm. Okay, cool. That makes sense.
All right. So now we know that this is equal to our s of our st function, but we have this like plus c over here. So here, let's move this over here. So we have s of t is equal to 36t minus 60 over t plus 1. All right, you guys can see that?
Yeah, but we can just see half of them. Like,
It's a little cut off.
yeah.
So which half can you see? The left half or the right half?
Well, we can see like, oh, we just can't see the top half of the thing you just wrote.
That a little bit better?
Yeah.
Oh yeah.
All right. So then, since we have this initial statement where s of 1 equals 10, right? So we're going to use that to find our c value. So we know that this equals 10 when everything else equals 1. So when t equals 1, this equals 10. And so we're going to use that to find what our plus c value is. So we have 36 times 1 minus 60 over our 1 plus 1, or 2. So then we have 10 equals, that would be 6 plus c. We'll minus our 6 over. We'll say c equals 4. So now we have our c value. And so now we're going to just take this equation and replace this plus c with our 4. And now this is our answer.
Okay.
So any questions about how we got there or what we did?
So from what I understood, basically we take the integral to find the original equation, and then we just plug in whatever they give us into the equation that we find in order to find c, and then we just plug in c, and that's your answer, like the original equation with c.
Yep. So yeah, so we're just going to use, so you're right, we just take the integral to find the original function, and then we use the initial value stuff that they give us. We use it in the equation that we found to find our c value, and that's basically it.
Okay.
And then you just rewrite it, I guess. Do either the other two people have questions? Or are you guys good? All right. So I guess we can just move on from that. And I guess the other thing that we wanted to cover was how to tell the difference between a linearization problem.
Yeah.
What's the difference between that and a tangent line function?
Yes, there's that one.
So I
And
guess
can you fix the camera? Like
right.
whenever every talks and it changes. I mean, not that one. Like I mean, the zoom camera. How do you say
Oh,
that?
it changes. So when
Yeah,
somebody else talks, it changes. I think you
yeah.
can change that just by clicking on the person that you want to. If you like click on the little three dots on the top corner of somebody's frames, you can pin the video,
Oh, thank you.
and then
Thank
it
you.
won't change.
Yeah, yeah, yeah. I figured it out. Thank you.
All right.
I had the same question too, so thank you.
All right, no problem. So I guess the difference between a linearization problem and a tangent line problem is a linearization, we're going to use the tangent line that we find to approximate a value, if that makes sense. So let's say we have like an equation y equals square root x. Now, a tangent line, we just find the derivative, so dy dx. That would be 1 over 2 square root of x, right? That's a derivative. And now, let's say we have this point 49, right? X equals 49. So now we know that y is going to equal 7.
7.
And we know that our slope is going to equal 1 over 14, right?
Yeah.
So
Yes.
this is our point, and this is the slope. And so now we can use the point slope formula. So y minus 7 equals 1 over 14 times x minus 49, right? And so that would be y equals 1 over 14x minus 7 halves plus 7. So that could be our equation. So what an approximation is going to say, so this would be finding the tangent line. What an linearization problem will say is they use a linearization to approximate what the square root of 49.01 is equal to. So if we didn't have a calculator, then this would be really hard to do, right? Doing the square root of 49.1 without a calculator. So this is basically how we do it without a calculator. So it's the same process, but now when we get down to this problem, we're just going to plug our 49.01 into our equation. And that's going to give us an approximation of what this equals. Like, kind of basically how it works. So if we think of this, we have a function that looks something like this. Oh, we have a tangent line. We just found the tangent line, right?
Yeah.
Well,
so the equation in the box just means tangent line, right?
Yeah. So this equation is this tangent line.
Yeah.
And if you like zoom in really close, if you just zoomed in, they're practically the same line. This becomes almost a straight line. And so we can say that if we plug in 49.01 into this equation, it's going to give us pretty much the same thing as if we plug a 49.01 into a square root. And if we want to do that, we can. So let's say that y equals 1 over 14 times 49.01 minus 7 halves plus 7. And I think, so if we plug that into a calculator, I'm pretty sure you come out with like 7 with something to some decimal. We'll figure it out. So I got something like 7.00714. And if we just take the square root of 49.01, we come out with almost, or 3 zeros, sorry. Then we come out with the exact same answer. So it's kind of like how we can use this equation and this equation. They will solve 49.01. But the farther away we go from this point, the less the same they're going to be, if that makes sense. So if we continued out on this line, the farther we go onto this line, the farther away we're going to get from the original equation. And so basically what a linearization does is it's for something like really close that would be kind of hard into something that would be at least a little bit easier to do by hand. So like, I don't know.
Sorry, but can you lower the camera?
Oh, yeah.
Oh, thank you.
All right.
Perfect.
All right.
I see.
So does that kind of answer your question about a linearization and a tangent line problem? They're essentially the same problem, but just with a linearization, they'll give you something like, approximate this value to this tangent line. And that works with like pretty much any function. So this could be some sort of like parabola function that looks something like this. And we could do the same thing where we have a tangent line right here. This is like x equals 2. And we could use this tangent line to approximate what x equals 2.01 would equal, or x would like 1.98 would equal. And we can use this tangent, a line function, instead of a parabolic function, which has a square in it. So parabolic functions are square, and line functions only have a single power. And then that becomes an easier problem, because then we're not going to have to square any of our x values. We can just plug them in. So that's all right. Before I erase it, do you have any more questions about this, or?
No, thank you.
Just a quick question. So on the tangent line problem and the linearization problem, do they usually give us one of the points? Is that right?
Yes. So a tangent.
Yeah, what do they usually give us? Sorry, that's my question.
All right, yeah. So a tangent line function, it will usually say, like, what is the tangent line of this equation? So let's say we have this equation, y equals x squared plus 3x minus 2. Well, they'll say, what is the tangent line at x equals -1? That's how a tangent line problem will be phrased. A linearization problem will be phrased, use this function to approximate, or like use a linearization to approximate what this equals.
Oh, okay.
So, so that makes sense then?
Yeah. So
Yes.
yeah, that made sense. Yeah.
All right. So I feel like we pretty much covered that topic. So,
Yeah.
I guess so. We have, so we covered linearization, tangent, and initial value. So we could cover like a min-max problem, a related rates problem, the area between two curves, definite integral, or we could cover some of the derivative problems and integral problems that are going to be on the test. What would you guys want to do?
Actually, I'm okay with other things, so.
So it's just that?
Yeah.
For me, would you be able to do a related rate problem?
All right. Yes, I can do a related rates problem. Okay, so let's say we have a cube, something like this. And let's say this cube has a square base. So say x, right? Let's say that it's got a base of 5 centimeters by 5 centimeters. And let's say we're pouring water into this cube at a rate of, let's do 10 centimeters cubed per second. And now let's say how fast is the water rising when h, or the height, so we'll say this is h, is 4 centimeters. And so let's say that's our problem. So one thing that's always helped me with related rates problems is to make sure I always write down the given information. So we also have to come up with a couple equations. So we're dealing with volume, so we want a volume equation here, right? So what's our volume going to be? What our volume equation going to be? Well, it's a cube, so we know it's just going to be all the sides multiplied together. So if it's a square base, it's just going to be x squared times the height. That makes sense? And then from there, we want to find a dH dt is what we want to find. And we know that dV dt, or how fast the water is changing, is equals to 10 centimeters cubed a second. All right. So knowing this stuff, now we can take the derivative of this problem. And something that I like to do to help me identify, help me take the derivative, because we have two different variables here, right? Which makes it kind of hard to do a derivative. So to really do this, they would have to be in single variables. But if we think about this problem real quick, our x, is it going to change how high the water is? So is how far across or how deep the cube is going to change the higher we go up? No, it's going to stay the same. So,
Right.
So we can just say that, well, this x is constant. Well, if that x is constant, we can just plug in our numbers right now. And so sometimes this x isn't constant. So if we have like something like a cone, as we go up, as the height increases, the radius is also going to increase. As h goes up, r goes up as well. And if that case, so if we had like the 1/3 pi r squared h for the volume of a cone, if we're doing something like this, well, this r, it's not constant, so we can't just plug in what our radius is. So, because this is dependent upon time as well. So in this equation, we would end up having to have a volume equation and some other way to relate h's and r's, so they'd all be the same variable. But since this is a constant, we can just plug in 5. That makes sense why that works?
Yeah, that makes sense.
All right. So then we can say our volume is equal to 25h. And now our volume, or dV, so when we take a derivative, it's dependent upon time. And our h, so instead of going to a 1, it does something like the v does. Since v is dependent upon h is dependent upon time as well. So they're both like dependent upon that time. So we're going to end up with dH dt. And then we have to solve for dH dt because that's what we're looking for, right? So we'll plug in our numbers now. So 10 equals 25 dH dt. So dH dt is equal to 2/5. Does that make sense how we got there?
Could you just explain that part one more time?
This last part?
Yeah.
So since we know how fast the volume is changing, so that's our dV dt is 10 centimeters a second.
Okay.
So we're just plugging in numbers here. And so like let's look at the question again. So how fast is the water rising when h is 4 centimeters? Does it matter how high you're up in the cube? No, because if you think about it, if you're like filling it up at the same rate, so if we think about it the same way as a cone, when you start filling it, it's going to fill really fast at the beginning, right?
Mm-hmm.
And as you get closer to the top, it's going to slow down. It's going to start filling less fast. The height's going to stop rising as fast. But in a cube, that's not the case, right? It just keeps going up.
Right. Yeah.
So this is a pretty simple related rates problem. The one on the test isn't much harder than this. Sometime pretty soon, I don't know if you've done the related rates with the cones and stuff. Those are fun. Those are okay, but it's not as hard as this stuff. It's a little bit harder than this, but not much.
Mm-hmm. Okay.
I'll just tell you to remember this constant thing that I was talking about. That if it's constant and doesn't change, then you can plug it in here. But if it isn't constant, then you have to wait until when we plugged in the 10 centimeters cubed when we plugged in all the other stuff. So I guess that's our related rates problem.
Cool.
So I guess we can just go to the next one, which would be probably the min-max problem.
Yeah, that sounds good.
So let's say we're building a fence around a new field. Let's say our field is going to be 3,400 square feet, or feet squared. And to conserve fence, we are going to build our field on the side of a river. So we have a river. Woo! And we're going to build a fence that's missing a side, so we don't have to use as much fencing. Let's say that these two things are equal, even though the picture doesn't show it. They are. All right.
Right.
So what are the dimensions on our field going to be to keep our 3,400 square feet, but minimize the amount of fencing we need? So this is what our problem is going to be. All right. So we're gonna need two equations to solve this. So first of all, we need to know what we want to minimize, which is the perimeter. We want to make sure that the perimeter is as small as it can be. So we know that the perimeter is going to be 2x plus y. But kind of what we're talking about, we have two variables here. So when we take a derivative, this is going to be a lot harder now that we're doing two variables. So we need to somehow replace one of these variables so it will be the same as y. And so we're going to do that by writing another equation that says area equals 3,400 feet squared. Well, we know that's x times y equals 3,400, right?
Yeah.
So now we can rewrite this equation to solve for a single variable. Let's say that y equals 3,400 over x. Well, now we can just plug this in. So our perimeter is going to equal 2x plus 3,400 over x. And now we can treat this as any other derivative problem, where min-max problem, where we take the derivative and set the derivative equal to 0. So we're going to take the dv dx, which is just going to be 2 plus, well, this is actually going to be minus 3,400 over x squared. That makes sense how I got to this step?
Let's see. Yeah, because it's 3,400 x to the negative 1, and so you took the derivative of that. Okay, yeah, that makes sense.
All right, yep. So now that we have this, we're just going to take this and set that equal to 0, right?
Right.
And now we want to solve for x, right?
Mm-hmm.
So we'll just add this to the other side. So we get like 2x squared equals 3,400, right? So x squared equals 1,700. X equals the square root of 1,700. I'll just plug that into my calculator real quick. And that's 41.23. So now we know our x dimension, right? So this is our x dimension. Now to finish the problem, or can you see that down there? Or do I need to adjust it? I guess to finish this problem, we need to plug this x value back into our area.
Okay.
Our area equation, because that would be the easiest way to get the y value. So now we can say that 41.23y is equal to 3,400. Well, now we can just divide and solve for y. So y equals, we take this 100. I get like 82.46.
Okay.
So now we know our dimensions. That keep the same area but minimize the amount of fence we have to use. Does that make sense? For all
Yeah.
we've done? All right.
Yeah, I think so.
Any other questions about any type of this problem? So,
So like the main steps, well, for this one, you had to figure out how to write that equation with the same variables, but that's just kind of like the word problem, and I think that's pretty common because I remember that in the homework, kind of having to do the same thing.
yeah, you've probably done problems very similar to this. But yeah, so like the important thing is being able to identify the two equations you're going to use, because you're pretty much always going to use two. Or so this one we had our perimeter equation, and then we had our area equation. So and then we use those to simplify our equations to just one. So we have two variables, we need two equations. Something that's also very helpful when we're doing stuff like this is always draw a picture. Pictures are very helpful, especially on like related rates things and on min and max things. Drawing pictures is very helpful. So that would be my advice for the test. All right, so you good with this one?
Yeah, that was good.
All right. So I know that we met earlier, and you had a question about Z substitution. And so I actually want to cover that real quick, if that's okay.
Let's do it.
All right. So like I said before, Z substitution is pretty much just a special case of a U substitution problem. Except for, so if let's look at an equation like this. Something like that. Let's say we have an equation like this. So if we're going to do a U substitution problem and we went through the steps, we're going to end up with this X here, right? So what we do is we're going to rewrite this equation. So we're going to say that Z is equal to X plus 12. But if we take the derivative of this equation, then we just get dz equals dx, right? So when the time comes, we can just replace this dx with a dz. But if we do that, then we get this. So if we do that, we end up with something that looks like this: x z dz, right? Well, what do you do with that? Well, you don't do anything with that. That's what you do. But you go back to this equation, and you can say, well, z is equal to, or x is equal to z minus 12. Well, so now when we rewrite our equation, so we're going to rewrite the x that we had out in front over here in terms of z. So we're going to end up with z minus 12 times z dz. And then this becomes a much more manageable problem because we can now multiply this into our x values. So then we have the integral of e to the 3/2 minus 12z to the 1/2 dz. So you can kind of see how it differs a little bit than a normal U substitution problem, because these are single variables, and so that's something that's pretty easy to identify if it's a Z sub or a U sub. If it's a U sub, this will be 1 power higher than the outside x. If it's a U sub or a Z sub, they will both be to the first power. That's the only time you'll ever use a Z sub, is when they're both to the first power. Because if they're both to the second power, you couldn't really rewrite it like this. You couldn't rearrange this equation without having the squares in there.
Okay, so they have to be both to the first power for Z sub.
Yeah. So Z subs are always going to be to the first power, and that's really the only time they work. And it's just a special case of U substitution where you go one step farther and you rearrange the outside variable to be Z's as well.
Right.
And so to finish off our integral problem, then this would just go to Z to the 5/2 over 5/2 minus 12z to the 3/2 over 3/2 plus t. And we got to make sure we plug back in. Since we started with x's, we want to end with x's. So we're going to plug back in our z's. So we have x plus 12 to the 5 halves times by 2/5 minus 12 times x plus 12 to 3 halves times by 2/3 plus c. All right, so that makes sense how we got there, and what the difference between a u sub and a z sub is.
Yeah. So
All right,
think-
because
it makes sense. Yeah.
yeah, because I remember you had a question about that, and I wasn't very solid in my answer. So
This is more solid. Thank you.
yeah.
Perfect.
Yeah. So I guess unless you guys have something else to cover, there's a couple things that I want to cover that will be useful on the test, if that's okay.
Let's
So-
do it. Yeah, I'm okay with that.
So the first thing that I've found, so I took the test myself, and the first thing that I found useful is to know how to rewrite root functions into powers, right? So if we have something like this, we can rewrite this as like x squared plus 1 to the 1/3 power, and so it is. So if we change this to be like a 4, and this was like cubed, we could rewrite this equation to be like x squared plus 1 to the 3/4 power. So this is kind of it's pretty simple, but I found that like knowing that kind of stuff really helped me on the test when I took it.
Yeah.
And some other things. So chain within chains, those are fun problems. So let's say we have like 4x squared plus 3 squared plus 4x cubed. So,
Sorry, David, could you move the camera just a little bit?
oh, sorry.
There you go. Perfect.
So, this is a chain within a chain, and these are pretty sneaky. Actually, I'll rewrite this one so it's even more sneaky. All right. So, like the first step, so we're gonna take the outside function, right? So we're gonna basically do the power rule to the 1 unit and then multiply it by the inside function. So we're gonna take this 3 times by the 4 minus x squared plus 4x to the second power, right?
Mm-hmm.
And then we have to chain it. So we have to multiply this by the derivative of the inside, which happens to be 4 plus, that's going to be the derivative of another chain function. So we're going to have this like chain within a chain, right? So we need to know the derivative of this function. So this is going to be 2 times 4 minus x 2 times -1, right? And I think it's just sometimes really easy to lose track of this negative here and to realize that when we do a chain here, we do end up with a -1. Whereas if this was like positive, we'd end up with just a 1. Sometimes they throw in a negative to throw you off, like a negative here. So you just gotta make sure you don't lose track of this -1.
Yeah.
All right, so, and then that's our problem. Then we could simplify it probably, but it's kind of hard. So we could multiply this out. So that's like 4 plus. Actually, it's not going to be plus or.
-4 plus x.
Oh well, then this is still multiplied by a -1, so it would be like 4 minus 8 plus
Oh, yeah.
x. So it's sometimes really easy to lose track of our negative here and make a mistake when we're doing simplification like this. So then that would be -4 plus 2x, and that would be multiplied by 3 times 4 minus x squared plus 4x squared. And I think that's about as simplified as you can get it.
Yeah.
Yeah.
Good.
So that was something else I noticed. don't lose your negatives. Remember, chains, even if it's just to a single power, this still has a chain since it's an inside function. So, like, it's still important.
Cool.
And aside from that, I would just make sure that you know your derivative rules, know the power rule. You need to know the chain rule, the power rule, the product rule, and the quotient rule. So I just brush up on the product and quotient rules. If you want, we could do. We have some time, so if you want, we could do an equation of like the product and quotient rule.
What were the other things on the list apart from derivatives and integrals?
So there's the linearization and tangent line problems, which we covered.
We did those, and we did the rates and the max and min.
And the initial value problem.
Yeah. Oh, so do we do all of those? I think we did, right?
Yeah, and so now I guess the stuff left other than derivatives and integrals, we have areas between two curves and a definite integral, and they're pretty much the same thing. So if we do the area between two curves, we'll cover the definite integral.
Yeah. Can we do that one to finish off?
Yes, that would be fine.
Sweet.
All right. So.
Oh, by the way, one of my groupmate is asking that if you are gonna share the link of this review session.
Yeah. So yeah, I'm recording this, so I will share the link. I'll convert the file and post it on YouTube.
Okay.
And
Great.
I'll send you the link.
Yeah.
All right.
Thank you.
So let's say we have our two equations. Let's say we have y equals x squared. This will be a simple one, and y equals x plus 2. Let's find the area between these two curves. So the first thing to always do when you're doing this kind of problem is to draw a picture. So it's gonna look something like this and something like that.
Yeah.
So we want to find the area in between these two curves, right? And so essentially what we're going to do is we're going to take the integral of the top and minus the integral of the bottom. And that will give us, because that gets rid of all this fluff on the outside, right? So maybe I should do that in a different color, but all this stuff on the outside, we're basically going to get rid of. Because if we just do the integral of x plus 2, we're going to get this whole thing. But when we do the integral of x squared, we're only going to get these corners. But if we minus the corners off of the whole thing, then we get the inside area. So like one of the first things you have to do is identify the x bounds, because we're going to do it with the x. So we're going to have this integral, and we're going to have this a, b. And it's always the top curve minus the bottom curve. And that's how you set it up. And now we need to identify these x boundaries. Since we're working with x variables, we need to know from what to what the x goes. So on this one, it's pretty simple to look at a graph and say, oh, well, it connects at x equals -1, right? And x equals 2, because that's where they intersect at. But a good way to check this is if you set these two equations. Can you still see this far right on the far left on the screen?
Yeah.
All right. So a good way to check this is if you can find where they intersect by setting the two equations equal to each other. Sometimes this means you end up having to do a quadratic formula, because sometimes you can't just look at a graph and see it. So you have to set this up, and if we really wanted to, we could do x squared minus x minus 2 equals 0. Or you could use the quadratic formula and get these same answers out. But if we plug these points in here, that makes the statement true. If we plug in a -1, that's 1. -1 plus 2 is 1, so that works. And then 2, so 4 equals 4, right?
Mm-hmm.
And so those are going to be our bounds. And the lower bound always goes on the bottom. So because we're going to go from left to right. So we're going to -1 to 2. All right. And now we're set up to evaluate our integral. So now we're going to do it. So we're going to have x over 2 plus 2x minus. And we're going to evaluate this at the points -1 and 2. So then we have 4 over 2 plus 4 minus 8 thirds. So and then there's a minus. The same thing with this -1 plugged in. So we're going to have this -1 or squared. So that's just going to be 1/2 minus 2 minus plus. This is still -1/3. And then distribute the negative. And so this is just 2. We'll rewrite this as 2. So that's 6, 8. So we have 8. And then this becomes minus 9/3, which is just 3. Minus 1/2. So we end up with like 5, 4, and 1/2, which is equal to 9/2. So you able to follow that?
Yeah, I think so. Just real quick, so you said you always do the upper bound minus the lower bound. Is that what you said?
You put the lower bound on the bottom. Yeah.
Okay.
If you do it the other way, you'd still get the same answer. It'd just be negative.
That'd be negative, yeah.
Yeah, so there's integral properties where we can swap these two. So we can put the -1 and 2 on the bottom, but then it makes everything negative. So if we put this negative up, so if we did this, we'd come out with the same answer.
Right.
Yeah.
Okay.
But so I guess that's pretty much it, unless you guys want to cover some other things. In my other review, we covered a couple derivative and integral problems. So if you want, you guys could probably also check that link out too. And I guess if you guys have any other questions, I think we'll end it here.
Yeah, I think I'm good. So you're gonna send both those links out in the email, or?
Yeah, sure. Yeah, that'll probably how I do it. I'll probably post an announcement. I'll have the teacher post an announcement on the link on the website, so you can go back and look at them a couple of times.
Cool. Sounds
Thank
good.
you.
All right.
Awesome.
No problem.
Okay. Thank
Good
you,
luck on
David.
the test. Have a good evening.
Thanks, you too.